So let's start off by describing what embodied intelligence actually means. Embodied intelligence refers to AI systems that don't just think, but can act. They can combine perception, reasoning, and physical interaction with the real world. It is the convergence of AI with robotics, with sensors, with hardware, which enable machines to touch, to see, to think, and adapt like living beings, so like humans. So let's start off with the panel. We have a very exciting panel for you here today. Would you want to start off by introducing yourself, what your company is doing, and how you are using embodied intelligence?
Yes. Hi, I'm Tara Javidi. Thank you all for being here. So I spent a big chunk of my career being in academia, working on trying to understand, in contrast to the existing AI solutions that we have, which they work on passive data that is fed to them. If you go really look at the physical world, you have to actually go out and seek information that can be used for learning and training. And that has been sort of an obsession of mine, as in the physical world, when there is no absolute notion of fidelity or resolution, how can you actually work with sensors that, on the other hand, are very much subject to the physical laws, come with a resolution, often come with a field of view, proximity tells you. So how can we integrate the physics of the sensing into the process of collecting the data and then use that data for building intelligent systems that can operate in the physical world? I particularly am really interested in large-scale systems, so that's a little bit more challenging than a narrow task of doing X or Y with a given robot. If you have a lot of devices, sensing devices that IoTs, for example, provide to us, how do you orchestrate the data coming in so that you can actually decide where to move the data, which robot to use to sort of get the kind of quality and fidelity of the data that will allow you to build intelligence out of that and monitor the footprint that we have on the planet, that I think we have done a pretty crappy job at so far. So I don't think there was a time where certain diseases were a thing of the past. So in my mind, really irreversible environmental damage as the cost of technology should become a thing of the past, and AI is really putting us in a position to do that.
Well, let's just say I am not qualified to talk on anything she is talking about today. But super good to be here. I'm Jacob Rodriguez. I was a student at MIT before dropping out with like 4 classes left, so I'm 2 behind this guy. And what I was doing during my studies is I was co-PI of a project called the Walking Oligomeric Robotic Mobility System that we worked in conjunction with NASA, the Big Ideas Challenge, and presented such project to people like Jeff Bezos at the Mars Conference. But the other take on this kind of general intelligence for robotic systems point is we understood that there was physical limitations to the hardware itself. So how do we create software systems that can design the hardware in the way that responds perfectly and adequately to the environment in which you're dropping it into? Taking that premise, we ended up starting a company, Oligo, which does this specifically for space-based systems. And that's how kind of my angle of responses will be taken in from.
Wow, those are some impressive resumes. Hey guys, my name is Michael Chen. I also was from MIT, where I did research on one of the first open source bipedal robots. During my time there, I realized how mature general purpose hardware is, and that the missing component was robot learning. This step change in artificial intelligence that enables robots to learn from human demonstrations, simulation, to be able to generalize across different environments, objects, whatever it may be. And I was obsessed with taking these 2 really step changes, the commercialization of general purpose hardware and robot learning, and figuring out a way to create an embodied AI platform that would actually allow you to implement these 2 technologies in real world services in industry. And that was the inception of Yandu AI, the company in which I am the CEO and co-founder of.
Very exciting. All right, so one thing in common between all these companies is you are building something in a lab and you're taking it to the outside environment. And for you, Jacob, you're taking it to space. All right. So what are the challenges that come with building a prototype, having something run successfully in a lab, and then deploying it in the real world? How are you navigating those situations. Jacob, do you want to start off?
So funny enough, one of our takes, if you saw me in the other room, we're trying to take this whole, everyone thinks, oh, spacecraft, space, it's really hard. We try to reduce it to an environmental engineering problem where you're able to determine what every single one of your boundary conditions are of performance and operation within that condition, which in this case is space. And frankly enough, building for space is a lot easier than it is to build a general humanoid like this guy is, right? So in our sense, we're, for context, building like generative design schemes to produce topology optimized structures. We're doing our own harnessing, trying to select like systems requirements. So a lot of our work on the research side is kind of how do the hardware engineers get all the requirements to build a robot that these two are now building general intelligence for. And in our case, we cannot trust our simulations at all. ANSYS, great. Any type of Siemens software, great. FEA analysis, we've seen those directly break down the moment in which you test it in a lab. So this whole sim to real gap that we see in robotics is probably the most true that we're seeing with the generative design space, specifically in satellites. There's a reason why a bunch of them fail. So a lot of our work is how do we actually create test as you fly conditions on the ground to make sure that we don't actually get this bird down.
Yeah, so to follow up on that, a lot of what we do as well is trying to simplify the problem as much as possible. That's one of, I feel like, the key steps of bringing something that the whole industry is really focusing on work in the lab and actually deploy it in a real warehouse. So right now we're working with our pilot customer, which is one of the largest 3PL in Los Angeles. And the way we're doing it is by, instead of focusing on having a robot that can mow your lawn and do your laundry and wash your dishes, we're focusing on one task. What that allows us to do is we can actually saturate the whole possible environment of all the different situations that robot would potentially encounter while doing a particular task in industry. And by simplifying that and focusing on less experimental ways of collecting data, like what Jacob said in simulation, for example, by sticking to real-world data and human demonstrations, we're able to actually bring something that can do real work in the real world, not a decade from now, but real useful humanoid robots today.
So I think for me, it's, I'm going to cut it across multiple things that it has been the challenge. The first thing in the physical, bringing AI to the physical world has been social in the sense that now you're building an engineering system, but you rely on a lot of software and AI. So kind of bringing the team to talk to each other, the complexities that are caused by building the software and so on. And it's somewhat related that there has been a lot of solutions. For example, our customers, if they have bought different kind of sensing technologies, they live in siloed spaces and their data is being uploaded. So it has been a challenge for them to even have visibility into all of their data as it belongs to the physical space. So you will have some disk somewhere that gives you all the humidity and gas readings somewhere, and then you have visuals somewhere else coming from cameras. So really building, and that has been our first product, really giving the ability to the customers to visualize their data in a physical space, coming from that physical space, and then allow the AI agent to sort of even orchestrate what you want to show to the user in terms of what things are critical, what are the data that needs the most attention at this point. So this has been really kind of cutting across boundaries, both culturally, because working with engineers as opposed to computer scientists, as opposed to AI folks, has been really fun, you know. And sometimes I joke with my engineers that they want to build from the beginning to the end of the system, and they don't leave any room that we're going to actually grow the system in ways that are unintended. So it's a lot of social teamwork added to the task, which I didn't expect in the first place, saying I'm going to build AI for the physical system. And then also just really going into the field and noticing how much data we're collecting in siloed, uncommunicable to each other, and sort of that has become a really big part of the project.
Very interesting. So it seems like the commonality is all of you, all three of you have systems deployed in very unique environments. You're going to space, you're in assembly lines, factories, and you're working with engineers directly. How do you prioritize the different environmental factors that go into engineering a safe system for each of these unique environments? How do you prioritize what has to be, what you have to optimize for versus, because there's hundreds of variables. Which ones matter?
That's a really great question that is constantly comes up as we think about this. Did I?
Oh, no, you're spot on.
It's just a hard question.
That's why we're both like...
No, it is one of those things that, so I have an AI group that wants to build systems that can generalize for all physical spaces. And then we have customers who don't care if we are building the new cool thing that will translate to some other space. They want to solve their problem. I don't want my refinery to have some valve leaking tomorrow. So where do you draw? And I think that the reality of it is a dynamic process. You work with what customers' the biggest pain is, at the same time in the back of our minds, as we have seen with AI, to really have the openness that don't overfit a solution to this particular application, right? So can we actually take the models to integrate? And for us, it's been easy because the pain point of the customer has been, I have lots of data, I don't know what to do with it, they're all siloed, can you help me make sense of it? So in some sense, they have been the ones who have begged us to give solutions that are a little bit more generic.
Yeah, I think so. The one thing I didn't mention is while I was still working at JPL, I worked directly with the co-founders of Field AI before they ended up starting the company. And this is where we worked conjunctly on like the DARPA subterranean program. We worked directly on the RACER program. And all of them had multimodal control schemes, different types of robots. However, their whole entire thing is basically like one model to rule every single robotic system. So when it comes to the environmental constraints, when we were still like basically building out how does your sensing scheme looks like, what does a long-range, mid-range, short-range planner look like, you basically have different definitive profiles for the hardware you work with. So after working closely with them, it's like, okay, we now have the entire same code base that was ported from a Spot robot, worked with that same templated code base that's working for an off-road like vehicle that's driving freaking 50 miles per hour in the middle of the desert going down like this massive canyon. And then I used the same exact code base and I got it to work for a 32 degree of freedom robotic eel that's supposed to go on the surface of Enceladus, right? So my take is after working with such crazy diverse systems, even in the robotics side, I'm highly convinced the software can be the same. It's like an operating system. However, I feel like the more people you talk to, the more end users, the more articles you touch, our investment, starting with space more specifically, is just like, we got to create the system to build the hardware specific to the application and let the software stay general. But yeah, I try to containerize the environmental conditions to the exact use case, but our software stack, even for spacecraft, stays generally the same.
Yeah, I mean, I think that's great. I'll just talk about the actual application. Whenever we're trying to deploy robots in a real warehouse, how do we ensure that safety? For us, the most important thing is demonstrating it working very well around no people at all first. So when we do our initial deployments, it's dark. So you guys have probably heard of like dark warehouses where there's no people around. And so we're able to deploy in a real customer facility and create value without actually having personnel that you have to worry about hurting potentially because a robot falls or hits someone on accident. And then having the right safety precautions in place so that people don't get too close to the robots and get smacked on accident.
That's actually a very interesting point, and it brings me to my next question. Do you think the systems you're building should augment humans, or should they collaborate with humans in any way? I can see a lot of challenges with non-deterministic. We all know AI is non-deterministic, right? So the challenge is, how do you have safety guardrails present to make sure that this system is right 100% of the time? Do you think it should just operate in silos like the dark warehouse you mentioned, or should be some sort of augmenting system?
Yeah, I think that the future resides in having human-robot interaction. And I think a big misconception people take when they're looking at robots that can do the same tasks people can do is they immediately jump to replacement. But in many cases with the customers we're working with, what's actually happening is reallocation. So warehouse managers, they are hair on fire, constantly running around. Their workers are constantly overworked and stressed. What they're missing is being able to actually tackle the problems that allow their businesses to grow. They're so focused on just the most basic tasks just to keep the business alive. So what we're hoping is that our technology enables warehouses and warehouse owners to be able to reallocate that labor towards things that are customer facing, towards applications that require the skills humans are really good at, like context switching, like problem solving, like creativity. And because of that, it implies that we need to have really good human-robot interaction for that to work, because everyone is working together alongside robots. We're not replacing them. And so a big part of that is going to be first demonstrating that it works in a dark environment, but then ensuring that the hardware, the software, every layer is designed in a way that is compatible to work with humans. I'll just give one example. Even the choice of actuators that you choose to work with matters so much. For us, when we source the robot manufacturers that we work with, we choose to use planetary gears instead of harmonic, because of the fact that when you operate around those robot arms, if it does collide with you, you could push it away instead of it providing so much torque that it actually hurts you in that action. So I think it's design choices at every level, from hardware all the way up to your highest level AI system that's doing the high level control.
Very helpful. All right, so we're coming up on time. If this panel was to reconvene 1 year from now, and we had the same exact crowd, we had all of you present, and we had all three of you, what is one advancement you would want to share about your startup that you feel like is not possible right now, but 1 year from today you would have that problem solved?
Our satellite's going to be in space. So it's pretty cool.
I think for us, our biggest thing is being able to do more than just one task. So right now what we're proving is by simplifying the general purpose robotics problem to do one task really well, that works. But now let's show it works for not just our initial application, which is bin picking in warehouses, but now let's move to packing. And if you can do packing, then you can do anything. And from there, it's like, if you figure out the formula for achieving manual labor automation within logistics within one task, you can apply that to any industry. And so figuring out that you're not just providing a service, but a formula, that would be my goal by next year.
So for us, we're in the business of building these adaptive foundation models, so data and building it for new spaces and its cross modalities of many different kind of sensors. This has not been done. So data is gold for us. So in a year, hopefully we have repeated these. We have some ongoing projects. We will have repeated enough to start seeing the cross-correlation between the kind of data that has been siloed, and for the first time we are getting to see their cross relationships.
Right, awesome. Well, thank you all so much for being here. And you heard you have to keep them accountable now. So we know exactly what they have to get done in 1 year. If they don't, we'll reach out to you on LinkedIn and bother you. But thank you all for listening. Thank you all for being here. And please give a round of applause to the panel. Thank you.